Hey everyone, this is Mr. Lee. In this video, I'm going to go over the center force model and the notes. We're going to approach this conceptually, and in class, we'll be doing a lot of mathematical practice. Now, this one is pretty heavy on the conceptual side and the notes side. So I highly recommend that you watch this first through without taking any notes, try to absorb it. And then the second time around, definitely write it down so that you have all the notes for yourself in class. Okay. And the reason why this is difficult is because up until now, a lot of the scenarios that we dealt with, we were moving in a straight line or in a parabolic arc. And so we are actually going to start to go a little bit more in depth about the objects that move in a circular path or a slightly parabolic path. Okay. So in order to have all that down, the concepts are the most important part. So let's begin. I'll be typing a lot instead of writing a lot. So definitely use the pause button on the video so that you have everything that you need. All right, so here's the important thing. If objects are what I'm going to call turning, okay, so the idea of turning is we're going around in a circle. There's a reason for it, and it's because of a force. Now, when we first did our forces unit, we usually said a force can either cause an object to speed up or slow down. And now we're going to add to that definition. So let's just write that down. Before now, forces caused objects to speed up or slow down. Remember, speed up or slow down, this is acceleration. Okay. That'll pop up later. But now we're going to add to that definition. Okay. But for this unit, the forces will cause objects to turn. Okay, so that's a big idea there. The reason why objects are turning is because there has to be a force. Now, this big idea here is objects want to move in a straight line with constant velocity. So this is one of Newton's laws. Okay, so now we can actually define this law. Newton's first law says that an object in motion wants to stay in motion. Okay, so basically, an object with constant velocity wants to have constant velocity unless there's a outside force, and that outside force will cause the object to speed up or slow down. So now we're adding to that definition. An object in motion wants to stay in motion unless there's an outside force, and that outside force can either cause it to speed up, to slow down, or to have a change in direction. So with that, we can add a new definition of acceleration. So acceleration is either speed up, slow down, or, and that's the big one for this unit, change direction. So the reason why we're focusing on changing in the direction is because we are not going straight, right? We're constantly turning. And that constant turning is a changing of direction, right? So if you were to imagine being in a car, your gas pedal speeds you up, your brakes slow you down, and the steering wheel is the other cause of the acceleration, and that helps you turn. So this turning acceleration, there's a definition. Okay, I won't call it turning acceleration because it's not the appropriate term for it, but that's like the best way to really figure out what's happening. The official term is called centripetal acceleration, where centripetal means center seeking. Now, that won't really mean much to us just yet because we're just going over definitions. But in order to solve problems, that definition of center seeking is, well, it's the most helpful thing that we can possibly use, right? So the turning acceleration is called centripetal acceleration, and there is a formula for it, and I'll write this formula down. So from the previous video, we learned that the net force formula, or the force formula, the generalized math formula, was V squared over R. Now, for those of you with savvy eyes, you may think, wait a minute, Mr. Lee, I thought force was equal to mass times acceleration. That should be V squared over R times M. And so if you take a look at the two formulas, you see a lot of similarities, right? You see a F here, you see a F here, right? You see a M here, and you see a M here. So that must mean that whatever is remaining has to be your acceleration. Okay, so I just want to prove it to you that V squared over R is your acceleration. So the units for acceleration is meters per second squared, just so you know. The units for velocity is meters per second, but we're squaring it. So we get meters per second, both of those squared, divided by the units for radius, which is meters. So meters squared over second squared divided by meters simply reduces to meters per second squared. So this middle term right there, I'm going to highlight it in pink, pink. That is your turning acceleration, or more appropriately named, your centripetal acceleration. So here's your first official formula. Centripetal acceleration, so that's a subscript c, and that subscript c tells us that we are looking at a centripetal acceleration is equal to v squared over r. Now, there is actually a little tiny subscript underneath of that v, and it's a t, and I'm going to go into the definition of what that t represents. So that t, so if that's my official formula right there, v sub t, imagine that's a subscript, means tangential velocity. Okay, so tangential velocity by definition is how fast you are going at the moment of time around the circle. So one way to think about this is if you're driving around the roundabout, right, or if you're making a turn and you were looking at your speedometer, okay, the speedometer tells you exactly how fast you're going at that moment, and that's your tangential velocity. Now, when we're driving a straight line, our tangential velocity is just our normal velocity. Okay, but when we're going around a circle, because we're constantly turning, that tangential velocity means how fast we're going at that instance around the circle. So if we take a look, if I were to draw like a path, let's draw the path in a light gray. So this is a path that a particle is taking to go around the circle, like so. Okay, and we'll say that it's going in this fashion there. And my object is right there. So if we were to freeze time and we were to just look at that object first, let's write this down. If time is frozen, okay, this is a huge moment. If time is frozen, there is no way to know that we are going in a circle. Circle. Okay, so let's say we have a particle and it's going around and around and around in a circle, but we were like freezing time, right? We push pause on time itself, okay? And there's no like dotted lines to show you the path that it's taking. There's no way that we actually know that's moving in a circle. But if I were to say, okay, are we moving with information knowing that we were moving in a circle, you'll say, yes, of course we're moving. And so the tangential velocity is the velocity that the object would be going or is going at in a moment of time. Okay, and the word tangent, in terms of math, right, is touching at one point, and the thing that's touching at one point would be the velocity vector, so vt. So the velocity vector touches the circular path at one point, and that one point is usually where the object is. Okay, so if we were going in a counterclockwise fashion, the tangential velocity will be just straight to the left. If the object was right here, okay, the tangential velocity would just go straight down, right? And I guess we'll just complete all of the sides there. When it's down there in the 6 o'clock position, it's going VT, and here it'll be going VT up. Okay, and that's because we are going in a counterclockwise fashion. However, if we're moving in a clockwise fashion, all of the directions would be reversed. So the tangential velocity is how fast you are going in a moment of time as you are traveling around the circle. All right. Yeah. Now, here's another important thing. Okay. So this whole unit is about why things move in a circle. So as a quick reminder, things move in a circle because there's a force. Okay, so here's a big moment, and there's a lot of questions about this idea here, so I want to make sure I pointed it out. If the force becomes 0 newtons, okay, so the force that causes the object to move in a circle becomes 0 newtons, then the object will no longer move in a circle, but a straight path, and that straight path is along VT. So meaning if there's no reason for this object to move in a circle, if it automatically just like stops, okay, the object will move in a straight line, and it'll be in the direction of the tangential velocity. And so I'll use a highlighter to show you, right? So let's say the top, if the reason for the object to move in a circle stops, it'll move along this path right there. Okay, it'll go flying out this way, or this way, or this way, or this way. Okay, depending on how it's being stopped. Okay. Oh, let me just show you an example of VT for a non-90 degree one. So if we have an object right there, okay, it'll touch tangentially like so. And I'll show you one over here. So if we have an object right there, the VT will look like this. All right, cool. So moving on with our notes, let's see. Let's actually get to the formula itself. So before this in the lab, we got the generalized math formula, but I want to give you the official formula. The official formula is sigma F, so it's the sum of all forces, a little subscript C there to let you know that we are looking for forces that cause an object to move in a circle, is equal to MAC. Now, if you remember for the FRQs, you always want to start off with this line here, okay, and you're going to list off all the forces. And in class, we'll get a lot of practice in identifying what the forces are, but just so you know, this should always be your first line. And the next line, so that you can get oftentimes your substitution points, you're going to substitute in to show the graders that you understand that centripetal acceleration is Vt squared over r with the rest of the forces there. Okay, now a couple important things. M is the object moving, okay, or in a circle. And I want to make this distinction because when we did the lab, there was a mass that was hanging, but because that mass that was hanging was not moving in a circle, that's not your M. Okay, R is the radius of the circle, and Vt, of course, we just went over. This is your tangential velocity. Okay. So with this idea here, I just want to make a distinction of our previous versus this unit. So in our previous unit, we said we use this formula here, F equals ma. And this model shows objects, so accelerating objects. Okay, so if you have an object that is accelerating, it's because there's a force. It shows accelerating objects, and it's either a speed up or a slow down. Okay, however, in our new model, basically the same idea, right? Even the strategies and the techniques to solve it is the same. Shows objects turning. Okay, and I'm gonna above it write the word accelerating, because both cases show objects that are accelerating. Okay, but we're just calling it turning for now, right? And so the steps are always the same. Okay, so always draw free body diagram. Okay, so always draw free body diagram. That's always step one. And step two is always use the net force formula. Okay, so the method of solving problems will always be the same. Okay, all right. Now, to show you a distinction between the two situations, I'm going to go back to a previous unit to show you an example problem of the steps above, so that you can see how there are similarities and differences. So let's say we have Fn, we have Fg, we'll call this F1 at an angle, and we have FF, and just so that we can have fun, there's also F2. All right, so we have multiple forces here. So the very first thing that you should do, okay, is you should identify the x and the y axes. So this is my y axis, and it's my x axis. And the reason why we want to do that is because if we were to create a f of y formula, okay, you only want to include the y forces. So in this case, we take a look at all the vertical forces, which I'll highlight, that one, this one, and of course we have this F1y component right there. I'm going to highlight that. And so our formula becomes f of n plus f1y minus f of g. And if we were to do that for the f of x, we would do the same idea. We would say, oh, I gotta create this in there. So this is f1x. We would say f1x plus f of 2 minus f of f. And according to the problem, we would just solve it accordingly, right? So that we have continuity's sake, I'll highlight all my x forces in this beautiful baby blue. I should use them more often. All right, so the idea behind centripetal forces is the same, right? You always draw a free body diagram, and then you progress from there. Now, the biggest difference between centripetal forces and regular scenarios up until this point is that we're moving in a circle. And so we are looking at a radial coordinate plane, but that sounds a lot more complicated than it is. So I'm going to draw the object, okay, and I'm going to draw the middle of the circle. I'm going to draw the circular path or the circle that the object could take, like so. Okay. So I'm just going to make up a couple of forces. So let's say we have F1 going up, we have F2 going down, we have F3 going to the right, we have F4 going to the left, and just so that you see this there, let's have F5 going off at an angle theta right there. Okay, so we have a total of 5 forces. Now, in order to set up a net force formula, so this is our free body diagram, is you have to identify the centripetal axis. Centripetal axis. So if you remember, the definition of centripetal is center seeking. Okay, so what you want to do is I highly suggest, if you have a highlighter or whatever the case is, use it until you get used to it. Go from the object and go towards the middle. Okay, just highlight all the way through and all the way out. So any force that is along this axis is a centripetal force. So my centripetal force formula for this scenario here would be, oh, I forgot to tell you what's positive and what's negative. So because it's center seeking, anything going towards the center is positive, and anything going away from the center is negative. So if we take a look at this, we can say that F4 is center seeking, okay, and it'll be positive. F3 is going away from the center, so that will be negative. And this F5 here, if I were to redraw F5 like so, we can say that this is Fx5 and this is Fy5, and only Fx5 is actually along the centripetal axis, so we can write it as plus F5 cosine of theta. Okay, and so the whole idea of up and down being positive and negative, left and right, positive and negative, all that goes out the window. The only thing that matters is that if it's center seeking, the forces is positive. If it's away from the center, it's going to be negative. And anything that is not along the centripetal axis does not matter. Meaning that only the forces along that axis actually causes it to move in a circle. So the idea here is that if you take a look at F1 and F2, F1 and F2. If those are not helping it move along the circle, what are those doing? So F1 will cause the object. So if I were to draw the velocity vector, right? So we know here, let's say the tangential velocity is going upwards. So what F1 is doing, so F1 is speeding up the object because it's along the same axis as V. F2 is slowing down the object because F2 is pointing down, but our V is going up. Okay, so F2 is slowing it down, and F5Y is causing it to speed up as well. So remember, centripetal, the hardest part about this is just realizing that it's the forces that cause it to move in a circle. We don't care about speeding up. We don't care about slowing down. That'll come later. And we just care about things that cause objects to move in a circle. And that's that. Those are the rules. It just takes some practice. And we'll get a lot of practice in. See you next time. Bye-bye.